Hello, let's start working on the Newton's law of gravitation. So far we have looked at the centripetal acceleration, which acts on the object moving in a circular path, and we know that most of the planets, they are moving in nearly circular or elliptic orbit. So if we want to know the centripetal acceleration of any of these objects, any of the planet, we can find it using the centripetal acceleration formula. For example, if you want to know what would be the centripetal acceleration for the moon, if we know the distance and if we know the speed, or we can figure out the value of the centripetal acceleration. Let's do that first before we could get the statement for the Newton's law of gravitation. Centripetal acceleration for moon, we can derive it using the formula that we have already known for centripetal acceleration, v square over r. Now, orbital speed for moon, yes, we can find it. If we consider that the orbit for the moon is nearly circular, we can apply v 2 pi r, which is the circumference of that circle, total distance. So if Earth is here and the moon is here, and the distance is something that we already know, and this is t. The total time it will take to complete one rotation, and what distance it will cover in one rotation, that would be 2 pi r. Where am I getting this formula? This formula is the distance over time for the speed or average velocity. So by using this formula, if we know the distance of the moon from the earth, and if we know how much time it's taking to complete one rotation, we can figure out the orbital speed for the moon. So I already know the numbers for the distance of the moon from the earth, and that is 384,000 kilometer. And the time period, the time it takes, so time period is not the time which we often talk about. It is the time when there is a motion which is constantly repeating itself, and in that case the time to complete one rotation on one revolution, one complete cycle, is called the time period. So this time is time period for moon to complete one rotation. So this is 27.3 days. Now this number isn't given in days, we can convert it to seconds in order to use it in order to find the orbital speed. So I'm going to plug this value in here. Let me call that A for moon. V is 2 pi r square divided by t square into r. So by using the values given there, I can figure out the value of the centripetal acceleration. Okay, so how do we convert the days to the seconds? I could first, so it's 27.3 days. How many hours in a day? 24 hours in one day. And how many seconds in a day? 30 seconds in in hour. 3600 seconds in 1 hour. Okay, by multiplying these with each other, we should get the value for the time in second, and that would be 2.36 times 10 to the 6, obviously you are going to get a very big number. Now this is the time period in seconds. It was given in days, and so if you Google this time for moon rotation about the Earth, you are going to get 27.3 days. For our calculation, we converted it to seconds, and we are going to use it here. Also, you do need to convert this to meter, and that would end up giving you 3.848 meter. So now we have our all these physical quantities in correct set of units. We can plug those in, and the number we will get is 0.00272 meter per second square. Now that's the acceleration the moon will need to stay in that. That's the acceleration for the moon moving in that circular path at that distance. Now if I compare it to g, by dividing it by g, I should be able to compare it with the value of g, which is 0.00. Yeah, if you divide them, you are going to get this number approximately. Okay, 1 over 3600. 1 over 3600 is going to be very close to what when you divide this number by 9.8, you will get this value for the relationship of the acceleration of the moon to the gravity at the surface of Earth. Now, what does it mean? Now, the radius of the moon, the Earth, is about, let me get the exact number. Earth's radius is about 6380. The radius of Earth is 6380 kilometers. And this distance, if I divide these two numbers for the distance of the moon from the Earth, I get about 60. So the distance, the moon distance is about 60 times the radius of Earth. So, in fact, we should have gotten, if the gravity is reduced, that is for sure reduced, because it's really at long distance from the surface of Earth. If the gravity was reduced with just r, then it should have reduced to 1 over 60 of its actual value. However, it has reduced more than that. That is the acceleration of the object at a distance of 384,000 kilometers from the surface of Earth. You could think of it as g is reduced to that value, and it is reduced to about 3600 of its actual value at the surface of Earth. That means it has reduced about 60 times 60, twice the distance. So we should, when Newton was working on it, by putting these points together, he was able to get a relationship for the force of gravity, or the forces between two objects. These are proportional to distance square instead, not just the distance between two objects. Also, there was another thought process. If this force is present between the object, then it depends on the distance. Why the normal object? Why don't we feel it? Why two persons? They don't. Why two people like you and me are not feeling it, it's because this value is so small because of our masses are small. So the other point was it is proportional to the product of masses. It becomes very important when we are talking about large masses. It becomes very negligible when we are talking about the object which are at regular distances from each other and they have the small sizes. It's mainly the size which is affecting the value of the force of gravity. By putting these two together, Fg would be equal to product of masses divided by r square if the proportionality changes into the constant. You have g m1 m2 over r squared. This is called connects any two objects separated by a distance r between their center of masses. If r is the distance between the center of masses, then there would be force of gravity by m1 on m2, and then there will be a force by m2 on m1. These two forces, according to Newton's third law, should be equal to each other and in opposite direction. G value is equal to 6.67 times 10 to the negative 11 Newton meter square per kilogram square. That's another reason we don't feel it, because the value of G is so small that the small size objects or small masses, they are not going to make much difference to the power of 10 here. Alright, so if you are putting 70 kg or 150 kg, that's not going to make very big difference here. However, when you're talking about the masses of the planets or moon, that's where, or mass of the sun, that's where this gravitational force becomes very dominant enough that it could keep the object in the satellites or the planets in their orbits. If we are talking about this force at the surface of Earth, we can also link it to the weight of the object that we are already familiar with. If something is sitting at the surface of the Earth, then the distance of this object from the center of the Earth would be RE, radius of the Earth, correct? The weight of the object would be would be acting downward, and there would be force of gravity acting on it. This force of gravitation which we just defined, which is acting on it. So the value of at the surface of Earth, this mg would be equal to force of gravitation. So mg, if I call this mass of the Earth me, this is m, then me small m, re square, which is the distance between them, big G, and this would give me, if I a formula for G in terms of gravitation constant. G would be equal to G m e over r, it should be square, e square. Now that is at the surface of Earth. So you can see the G depends on distance now. So if you know we already know the value of big G, that's the gravitational universal constant. ME is the mass of the Earth, RE is the radius of the Earth. By plugging in these values, we can also find out the value of acceleration due to gravity, and we already know it should be 9.8 meter per second square. That's another way to approach the this physical quantity. Now, when this is on the surface of Earth, however, if this object is raised, let's say it's moved up, the G value is meant to decrease. So at higher altitude, the value of G is decreased, but at the surface of Earth, we can use the value for G that is known as the 9.8 meter per second square, but Just keep in mind that it changes with the distance. As you go away from the surface of Earth, the higher you go, the value of G will decrease because it's inversely proportional to the distance of the object from the Earth. I'm going to end this video here. You will see me again in my next video. Thank you.